So now that we have talked about thin lens and we introduced the lens maker's formula, the lens equation, the Gaussian lens equation, I want to tell you about ray tracing and magnification. And the point of this is, so far we've been considering only those rays that were emanating from points that were exactly on the axis. So if you go back to our earlier derivations and our earlier expressions, we always looked at points, say S, which was right on the axis, and as you may remember, we showed that these rays, for example, will go and converge to the point P over there, which is also on the axis. But what happens for real objects is that they might have a dimension which is extended above the optical axis, right? So for example, the filament of your bulb or some laser spot, whatever it is, may not be exactly just a point on the optical axis. It may extend above that. So we want to look at those rays that emanate from objects that are off axis. And so to do that, we do this ray tracing, which will help us to also understand the magnification of a lens. So first of all, I draw your attention to the cardinal points, which are the focal position on the object side, the focal position on the image side, and also the center of the lens, which is O, as drawn here. Okay, those are the 3 points of the lens that are important. Even though I drew the lens with a finite thickness, we know for a thin lens it doesn't matter. The lens can essentially be thought of as just having one place, O, where the lens intersects the optical axis. And now here we have the object S1 over here, and we are going to trace, and the object S1 has a height which I'll call Y0 or YO, which is above the optical axis. Okay. And as usual, the image convention is SO is going to be positive, SI is going to be positive, because both SO is to the left of the lens, SI is to the right of the lens, so those are both positive. And similarly, you also see that we can draw a couple other dimensions and distances over here, which I want to tell you about the sign convention for those, which is for the distance between the focal length and the object is called XO, right? As you can see on this drawing, XO is the distance between the object and the focal length. And similarly, XI, right? And so the convention is, again, just like for object, XO is positive if it is left of the focal length F0, FO, which is the focal plane on the object side, and XI is positive if it's to the right of F sub I. Okay, and YO, the object height, is positive if it is above the axis. And YI is positive if above the optic axis as well. So we say that YI, if YI turns out to be negative, we say that the image is inverted with respect to the object. And if it's not, we say it's upright or erect with respect to the object. Okay, so now that we've introduced the sign convention, I want to draw your attention to 3 very important or chief rays that we will use in optical ray tracing, at least on this in the part that you can do on paper. There are ray tracing programs that I'll tell you about later that one can use. But when you're trying to trace rays for the first design of an optical system, these are the 3 chief rays that one draws. The first ray is a ray that emanates from the point that is off axis, which is this, is this object over here, and we draw it parallel to the optical axis. So you can see that's the ray 1, and that is parallel to the optical axis. And then we know that a ray that's parallel to the optical axis from the object side will hit the focal plane on the image side, and we show the bending of that ray as if it happens all at this point, which is right on the center of the lens, because the lens is thin. So we may as well just approximate as everything is happening right at the center of this lens, and that's where the ray tracing is done, so that it goes right through that image plane over there. And then we have the second chief ray, which goes through the center of the lens, and this ray is completely undeviated. It passes straight through from one end to the other and just continues without any refraction at the interface. It can be shown that every lens has such a point. Even if it's a thick lens, there is a point inside the lens such that if you send in a ray at the right angle to intersect that point, then the ray will emerge with no change in angle. Okay, and finally we have the third optical ray, which is going through the object focal plane, and then when it hits the lens, we know that such a ray must come out parallel to the optical axis, which is what is drawn here. All three rays will intersect at a point, and that point will form the image of the object point that is off axis. And of course, the image point, the object point that's on the axis will be imaged to the point P1 over here, which is just using the Gaussian lens formula as before. So the object point here and here presumably will image at the same point, same distance, from the center of the lens. But if the question now is how much is YO and YI, so if YI is the image height, how are they related? And to solve that, we just need to look at these triangles which are over here. So I will draw your attention first to the triangle AOFI. Okay, so this is this triangle AOFI. And by the way, let me also give some names or some labels to these points. So this is S1, which is right on the axis. S2 is the point from where the rays are coming out at the top of the image, and P2, or the P2, which is over here, is this point over here where the rays are meeting. Okay, so S2 and P2 are object and image or conjugate points of each other, just as S1 and P1 are conjugate points for each other. Okay, so now let's look at the triangle AOFI. Okay, so that is this triangle, and maybe I choose a slightly different color. Okay. Oops. Okay. And the triangle which is over here, maybe I should make this a little thicker so that you can see it better. These two triangles, okay, which are highlighted in green. I claim that these two triangles are similar. That's because this angle over here and this angle are the same, right? When two lines cross, the opposite angles are always the same, and the other angle over here, which is 90 degrees, is also the same. So two angles are the same, which means the third angle is also going to be the same, and that's all you need for similar triangles. Okay, so if that is the case, the YO divided by Y, remember that this height over here was very carefully picked to be the same as the height YO over there, and and similarly YI is also picked to have the same, is clearly the height of the image. So now we can make the statement that because these two triangles are similar, the ratio of these two sides, that is the sides that are vertical, is the same as the ratio of the sides that are, say, horizontal over here and here. Okay, so we can and again, by the same argument, we've already established that the distance from O to Fi must be F, the focal length, and the distance from Fi to P1 must be the distance Si minus F. Okay, so we can right away write Yo divided by the magnitude of Yi is equal to F divided by Si minus F. Okay, that's equation 1. Similarly, by the exact similar argument, I can look at this big triangle over here, which is all the way from the object up to the point O, and then similarly I can look at that triangle over there, which is all the way from the object, the point O, to this points P1 and P2. So the triangles S1, S2O and P1, P2O are also going to be similar for the exact same reason, and therefore we can make a similar argument. Now the two sides that are in the right ratio are this side over here and this side over here should be the same as this side and this side, right? And the distance of this side is SO, the distance of this side is SI. The YO divided by YI should be SO divided by SI, and therefore we can equate from equation 1 and 2. We have SO divided by SI is equal to F divided by SI minus F, okay, which just simply retrieves for us, if you solve this equation, 1 over F equals 1 over SO plus 1 over SI. So we've rederived the Gaussian lens formula by this ray tracing argument. So that's nice. It tells us that the ray tracing is a good way, is correct, because it gives back a formula that we derived through other means. But furthermore, it also helps us to see that the magnification Yi divided by Yo is simply equal to Si divided by So in magnitudes, right? So if you're just simply calculating the magnitudes of the magnification and the sign, as I said, we can see it from this equation, is going to be dependent on whether the SO and SI end up being having the same sign or not. If you're confused about that, we can always define the magnification. So now that we have calculated it, we can define a certain sign convention for the magnification, which I call the transverse magnification, because it's the one that's up and down, right? It's a transverse to the axis. So I'll simply call that Yo divided by Yi divided by Yo. So that's so that takes into account all these sign conventions. And because, as we can see from this formula, that from this ray tracing, that it's the negative of the magnitude of Yi, we get that this must be minus Si divided by So. Okay. Again, remember I told you that the convention is if the transverse magnification is going to be negative, then if MT is lesser than 0, then we have an inverted image, as you can see from that drawing. And if MT greater than 0, we have an upright image. Okay. We can also derive one more expression. We can look at one more set of similar triangles, which is the ones that are over here. So this is a similar triangle over here. Sorry, I've redrawn too many times here. So let me choose this guy, this guy, and this guy, and this guy, this guy, and this guy. So if I look at that set of similar triangles, we can actually write that FO divided by SO minus F is equal to, again, Yi divided by Yo, because now we see in this triangle, this distance over here from O to this point B over here, this point B has now become obscured, so that's point B, it's point A. OB is the same as YI, so that distance is YI, and this distance is YO. So again, the ratio of those two sides, the ones over here and the one over here, must be the same as the ratio from here to here. And this first one is focal length, the second one is what I called XO, and therefore we get that FO divided by XO is equal to YI divided by YO. And I'll call this equation, let's see, I have equation 1, 2, I guess I could call this equation 3 because that's the Gaussian lens formula. But from equation 1, we have that YO divided by YI is the same as F divided by SI minus F. So if I call this equation 4, from 1 and 4, equating 1 and 4, and remember SI minus F here, this quantity over here is simply XI, okay? Therefore, XO XI is also equal to F squared, okay? And this is a nice, again, simple way to know where your image and object are going to be relative to the focal point of the lens. Okay. Okay. My last sort of comments about lateral magnification, which is given here, is that for real objects and real images, SI and SO are always going to be greater than 0, which implies all real images formed by a single positive lens or formed by a single thin lens will be inverted by our definition of when the magnification is positive and negative. Okay. We can also, one more, by using that formula for XO and XI that I just derived, leave it as a pretty straightforward exercise, is that it's possible to show that this is also the same as these ratios over here. Okay. Finally, we can also do something called the longitudinal magnification. So what is the longitudinal magnification? Well, so far we took the object to be extended perpendicular to the optical axis. What if the object is actually extended not perpendicular to the optical axis, but parallel to the optical axis? So imagine that it's some kind of thin rod that is extended from S1 to some point S2, but the S2 is now lying along the optical axis rather than perpendicular to the optical axis. Well, for that, what we need is so-called longitudinal magnification, which says how much does XO is now the variation of the position of the object, right, along the optical axis relative to the focal plane. XI will be similarly the ratio, the variation of the image point on the optical axis with respect to the focal plane. So if we know dxi over dxo, which would be the same as dsi divided by dso, right? Dxi divided by dxo, which is equal to, from our formula for the XO XI, we can immediately calculate this is minus F squared divided by XO squared, which because of this above formula over here is the same as minus transverse magnification squared. So this is a very general result actually, although I've derived it for the specific case of a thin lens. The longitudinal magnification ends up usually being the square of the transverse magnification. Okay. So at this point, I'm going to pause the video and I'm going to ask you to answer